All right, so, okay, I defined the Weil algebra, okay, associated to a principal bundle with a connection. Yeah, so G is a Lie group where with Lie algebra little g. Okay, so it's any Lie group. Yeah, I'm not assuming that it's connected. And the Weil algebra. Oh, okay. Now let's say we have a basis for the Lie algebra. So, and the dual basis alpha 1 to alpha n. Then, okay, the Weil algebra is the exterior algebra of G dual tensor with the symmetric algebra of G dual. Okay? Now what this means is that the exterior algebra is generated by alpha 1 to alpha n. Okay? And the symmetric algebra, that's the polynomial algebra generated by alpha 1 to alpha n. Yeah, so in the exterior algebra, alpha I wedge alpha j is minus alpha j wedge alpha I. And in the symmetric algebra, they commute. Well, you know, to distinguish between these two, let's see, introduce this notation. Let theta I be alpha I tensor 1, okay, in the exterior algebra tensor with the symmetric algebra, okay, in the Weil algebra. And UI will be 1 tensor alpha I, okay, in this. Okay, so the theta i's are anti-commutative, and the ui's are commutative. Okay, and then yeah, then the Weil algebra, it's you can say that it's generated by theta, the theta i's, and the ui's. Okay. Yeah. And then we make this into a graded algebra. So we give the Lie algebra a grading by, say, the degree of theta I is 1, and the degree of ui is 2. Okay? And so this way, in fact, you can say that the Lie algebra is the exterior algebra generated by all of these, because the degree of ui is 2, so they will commute, right, in the exterior algebra. Okay. And we have defined the Lie map. F from the exterior algebra to differential forms on P. Okay? And now, similarly, we can define if omega is the curvature of the connection, and P is in P, then the curvature is a two form. So it takes two arguments, and it gives you a real, and it gives you G, because the curvature is a G value 2 form. Okay? And now, if alpha is in G dual, you can follow this by alpha. And you will get a R value 2 form. On P. Okay. So this gives you a map. F from G dual into two forms on P. And then you can extend it to an algebra homomorphism. On the symmetric algebra to forms on P. So the symmetric algebra is the polynomial algebra generated by, now I'm calling them, this is isomorphic to, I'm calling them U1 to UN. Okay. And so F of UI1 to UIK will be F of UI1, which F of UIK. But this is a product of two forms, so they will commute, okay? And so it's well defined. If you change the order of the U's, you get the same thing. Yeah. And, yeah, so we have a bilinear map F from the Cartesian product to differential forms, right? Yeah. So if you have an alpha here and a beta here, so you send it to F of alpha, which F of beta. And because it's bilinear, then it gives you a linear map. There is a linear map from the tensor product to differential forms. Okay? Now here, the tensor product is over R. These are all R modules. And that is the Weil algebra. Okay? So this is called the Weil map. And this map, see, we want this map. Now, so far, this map is an algebra homomorphism, but we want it to be a morphism of G differential gradient algebras. Okay? Okay, that means it should commute with the exterior derivative and with the actions of the Lie algebra and the Lie group. Okay, so let's first try to define the exterior derivative. Now the exterior derivative, okay, it will go from the Weil algebra to itself, but it will raise the degree by 1, okay? And then the Weil maps it to omega p. So this should commute. Yeah. Now, so let's write out the Weil map in terms of generators. Okay. So with respect to a basis x1 to xn for G and dual basis alpha 1 to alpha n for G dual. So let's see, what is the Weil map of, oh, okay, now it's going to be confusing because the alphas, if they are in the exterior algebra, they anti-commute. If they are in the symmetric algebra, they commute. So I'm going to write theta I, okay, for the alphas in the exterior algebra. Okay? Then f of theta I is theta I composed with omega. Okay? Oh, and then omega, yeah, maybe I should first write out omega. So omega is a linear combination of omega I xi. Capital omega is a linear combination. Okay. And then f of theta I is theta I composed with omega. So theta I composed with sum of omega I xi. I probably should call this, let's call this K. Okay. And what is that equal to? Yeah, this is going to be, you see, this, if you apply this to a vector, this is a number, okay? So it just comes out, and so this is going to be omega I theta k xi, and that's a Kronecker delta, so you'll just get omega k. Everything is 0 except when I is equal to k. Okay? And then f of uk is uk composed with big omega. So uk and that will give you omega k. Okay? Yeah, and that tells you how the Weil map acts on the Weil algebra. Okay. Yeah. So. Okay. Now. Okay. So now to define the exterior derivative, you just have to define it on the generator. Right? Then you extend it as an antiderivation. Okay? So I have to know how to define d theta k. You see, you want that diagram to be commutative. So theta k, it maps to d theta k. And here, f takes it to omega k. And then omega k maps to d omega k. Right? And so d theta k has to go to this. Okay. But what is d omega k? Hmm? Uh-huh. Yeah. So by the second structural equation, omega k, the curvature, is d omega k plus 1/2 the sum of Cij omega I wedge omega j. So d omega k is the curvature minus 1/2 Cij omega I wedge omega j. That's d omega k. And F is an algebra homomorphism. Okay? So what element here will map to this? So for F to preserve D, we must define d theta k to be equal to, it has to be something that's going to map to that. So what's going to map to this from the Weil algebra? UK minus 1/2 the sum of Cij theta I wedge theta j. Yeah. Yeah, so that has to be the definition of the exterior derivative on the Weil algebra. And then if you look at UK, so UK maps to omega k. And then duk, so it has to map to d omega k. Okay. And what is d omega k? By Bianchi's second identity, yeah, I mean, Bianchi's second identity d omega is bracket omega little omega. So that means if you take the kth component, it's going to be the sum ofCijk omega I wedge omega j. Right? If you take, so this is the sum ofCijk omega I wedge omega j. And so duk it has to be something that maps to this. So we must define duk to be the sum ofCijk ui theta j. Okay, so that's the differential on the generators of the Weil algebra, and then we can extend D to the Weil algebra as an anti-derivation. So because the Weil algebra is freely generated by the thetas and the u's, you see, you can extend it, okay? It will be well defined. Okay, so now, okay, the Weil algebra has a differential. Okay? And this differential, it raises the degree by 1. Okay? theta has degree 1, u has degree 2. This is degree 2. Okay? Yeah. And then here, this has degree, u has degree 2, but this is degree 3. So it's an antiderivation of degree 1. It raises the degree by 1. So this makes the Weil algebra into a differential graded algebra. Okay, and now we also have to define the action of the Lie algebra on the Weil algebra. So, and again, we just define it on the generators. So you want to define IA and it should commute with the Weil map. Okay. So if you have theta k, IA of theta k, and theta k goes to omega k, IA of omega k. Okay? Now, IA of omega k, by definition, is A bar of omega k. Oh, yeah. And what is this? Omega k is a one form, right? And A bar is a vector field. So what's the definition of interior multiplication? Yeah, this is going to be a function, and it will be simply omega k applied to A bar. And and actually, you know that it will be a constant, right? Because, yeah, omega applied to A bar is simply A by one of the properties of a connection, okay? And so if you write A in terms of its components, it will be theta k A xk. And so this omega k bar is equal to the constant theta ka. Now the Weil map, it takes a constant to a constant So we must define IA of theta k to be theta ka. Then this diagram will commute. Okay. So that's how we define IA. Okay. On the Weil algebra. Okay, now what about the other generator? Okay, IA of UK. So UK goes to omega k, the curvature. And IA of omega k is IA bar of omega k. And what is that equal to? You know, A bar is a vertical vector field. It's zero, right? Because omega, the curvature is horizontal. So this must be zero. Okay, now you know how to define IA on the generator. Again, you can extend it to the Weil algebra. As an anti-derivation. Okay, and IA is going to lower the degree by 1, right? Because it takes a 1 form to a constant. Here it takes a 2 form to 0. With 0, it could have any degree. So now you have IA, and then finally, we define LA, the Lie derivative by Cartan's formula, DIA plus IAD. Okay? And because both D and IA commute with F, the Lie derivative will commute with F. LA will also Now, if the group is connected, then a form is invariant if and only if the Lie derivative is 0, right? We proved that before. If the group is not connected, then that's not true. And then, yeah. So now I also have to define the action of the group. Okay, yeah. So if G is in G, I need to define RG star of theta k. Okay. Now, okay, so theta k goes to omega k. And then, what does RG star go to? Yeah, so RG star of omega is at G inverse of omega. And so you just need to take the kth component with respect to the Lie algebra. Okay. And then that's what this should go to. Okay. So that means, so we define RG star. You see, yeah, probably we should just say let theta be the sum of theta k xk. Okay, and then we define RG star of theta to be at G inverse times theta. Okay. And then, so RG star of theta k, it will just be the kth component. And then, now RG star, okay, so, yeah, it's an algebra homomorphism, right? So you just extend. Oh, and then, yeah, RG star of UK will be the kth component applied to U. So you let U be the sum of UK xk. Okay. Okay, so now I know how to right translate the generator by RG star, and I extend it to an algebra homomorphism. So extend star to the Weil algebra as an algebra homomorphism. Okay? So this makes the Weil algebra into a G differential graded algebra. Okay, so what we are doing here is we're trying to construct an algebraic model for equivariant cohomology. Okay? So next time we will compute the cohomology of the Weil algebra. See, because it's a differential graded algebra, you can compute its cohomology. And we'll show that the cohomology is trivial. Okay? So it's 0 in every dimension except in dimension 0. And so it has the same cohomology as the total space of the universal bundle. Okay? And so the Weil algebra will be the algebraic model for the universal bundle. And then the equivariant cohomology of a space, right, is the quotient of the universal bundle times m. And so that will give us an algebraic model upstairs. And then by looking at the basic forms, we get an algebraic model for equivariant cohomology. Okay. And then the theorem will be that that algebraic model actually gives you equivariant cohomology. Okay? And that's the equivariant de Rham theorem. Okay? Okay, so we will continue next time. And next time we will compute the cohomology of the Weil model.